In order to quantitatively analyze electric machines, we first need to set up a coordinate system. A coordinate system is a scheme to uniquely identify locations in space. Our natural choice would be to use a Cartesian coordinate system. The side view of the machine is shown in this slide. The axis of rotation of the machine is chosen as a z-axis, and O denotes the origin of our coordinate system, and the y-axis is also shown. The x-axis comes out of the page so that it forms a right-handed system. The front view of the machine is shown. This is basically a slice of the machine at z equal to 0. The z-axis comes outside the page so that it forms a right-handed coordinate system. As the machine structure has a cylindrical symmetry, slicing the machine at two different z coordinates would give us identical slices. The machine's behavior therefore should not depend on the z coordinate of the point. As the machine's behavior is independent of the z coordinate, we can focus only on the front view of the machine. Consider an arbitrary point P whose location is at x1, y1, z1. The slice at z equal to z1 is shown. There are three regions which are of interest to us. They are 1. The air gap, 2. The stator inner periphery, and 3. The rotor outer periphery. The air gap is of interest to us because it is only the air gap magnetic field that is responsible for energy conversion. And stator inner periphery and rotor outer periphery is also of interest to us because the conductors are located in these regions. The above three regions are almost at a constant distance from the machine's axis. This is because the air gap is very small. So this motivates us to use a cylindrical coordinate system rather than a Cartesian coordinate system. Instead of using Cartesian coordinates x and y, we can use polar coordinates r and phi to locate the point P in the plane z equals z1. The polar coordinates r1 and phi1 are related to the Cartesian coordinates x1 and y1 as shown below. The unit vectors are the building block vectors for a coordinate system. There is a unit vector associated with each coordinate. R hat is the unit vector associated with the r coordinate, phi hat is the unit vector associated with the phi coordinate, and z hat is the unit vector associated with the z coordinate. Let's draw the unit vectors at location P. R hat is a vector whose length is 1. It points along the direction of increasing r coordinate but without changing the phi and z coordinates. Similarly, phi hat is also a vector of unit length and it points along the increasing phi coordinate but without changing the r and z coordinates. An important point to note is that the unit vectors r hat and phi hat are position dependent. This aspect is evident from the unit vectors at locations A, B and C. Clearly, r hat at location A is not equal to B is not equal to C as they all point in different directions even though all of them have unit length. A similar argument holds for the phi hat vectors at A, B and C. This is unlike a Cartesian coordinate system wherein the unit vectors don't change direction. They are the same at all locations. So I cap at location A is same as B and same as C and similar for J cap. Using trigonometry, we can write the unit vectors r hat and phi hat in terms of the unit vectors I hat and j hat. So from this, we can clearly see that the unit vectors depend on the phi coordinate of point P as it depends on cos phi 1 and sin phi 1. So this explicitly shows that the unit vectors r hat and phi hat are indeed dependent on the position of the point. Thank you.